about that foundation. I think it's important that we understand what kind of an environment that we're looking at and what kind of tools we have available to address security. Then I will focus specifically on the aspects of security, how they can be addressed within such a model execution context. And it's most useful to discuss cases that actually use such an approach. This is not something, this is not a theoretical exercise, this is something that we use today almost since 4 or 5 years. In IT terms, this is half an eternity already, but it is still relatively unknown. For about 2 or 3 years ago, there was a paper by Neil MacDonald from Gartner, who for the first time tried to coin the term model-driven security. There's still not many vendors out there that address this in a commercial way. So it will be certainly interesting also for me to engage in a dialogue with you afterwards. What do you think about these concepts, these ideas as they relate to your personal point of view and also the challenges that you are facing? So we'll finally conclude with my view of the benefits of this approach. We tend to be blindsided to the disadvantages when we try to promote a particular approach and concept, but I'm sure this has all strengths and weaknesses, and of course this is all work in progress. So to get started, let me talk about the foundations. The concept and idea of executing models may not be so familiar to you because it is still something that is not widespread, it is not mainstream. Model-driven development becomes mainstream. It's getting more and more important every day as we attempt to automate certain ways of software development, and also as we try to get a handle on the quality of the software that is being developed. Automation always being a good way to be consistent about the way that we do things and how we can employ best practices in the process and hide them as part of the machinery. Now, most software developers, several million around the world, are using one or another type of model to specify software. When we want to design complex systems, it is fairly natural to use models as a means of communication during the design and architectural stages. Now, it would be ideal to be able to continue that throughout the entire life cycle of software development. That is, of course, reality teaches us not always the case, because typically from design we walk into implementation, then we walk into testing, then we go live, and then the maintenance cycle starts. And somewhere in the middle, whatever the reason is it a lack of time or a lack of discipline, certainly not a lack of goodwill, we start to lose the connection to the initial design frameworks and the documentation or the specification as we hurry towards the deadlines where quite often projects are running out of time, running out of money. These are the reality factors that we all have to deal with, be it on the end user side, being on the service delivery side. It's always a challenge. So we're in this industry, the individuals that work here at E2E since some 20 plus years. We've seen all sides of the table. We were end users first, then we were systems integrators, now we're a product company, but the point of view changes, but the ingredients, they never change. And one of the fundamental problems we try to solve is finding a way that across the life cycle of software development and maintenance, that we can find a way that the production systems that we eventually create are documented in the way that they're actually used. If you look around real companies in this world, this situation is unfortunately not the regular case. You will probably have a hard time finding a company that uses software for business critical applications that can truly say, yes, what we have running in productions, every single concept we use there to a sufficient degree of detail is documented as used. That's still considered best practice, but it's in reality a rather luxurious position to be in. Now, what we asked ourselves some 10, 15 years ago, isn't there a possible way to change that situation where we have to say, well, unfortunately, the code or the source code that we have for all what we call legacy applications today is the only kind of documentation we got. It's clear that is not sufficient. So is there a way to turn this paradigm around find a way that makes it natural for developers to live in a software lifecycle where the documentation is the code. Now, model-driven development shows us a pointer since many years, since more than 10, 15 years, in a variety of forms. In 2000, the Object Management Group has promoted the concept of the model-driven architecture in an effort to increase the quality of software development in heterogeneous complex environments. We've essentially taken those ideas and we brought them down to practical use in a sense that we do not only use models to generate software artifacts partially or completely, but that we also use models on the execution side. Naturally, once the machine executes the models, there is no graphical context anymore, but the specification is so directly linked that you then begin to change and adapt software at the level of models and not at the level of code. Now, when I say that, typically when we use model-driven approaches, we speak about code generation. So out of the models, some other form of artifacts are being generated, typically Java, COBOL, C, C++, another type of high-level programming language. And this has been the state of the art for quite a while. And it's an approach one can take, but it has also severe drawbacks. Automation always, when you try to pack things into transformation routines to go from models to code, typically you end up generating automatically a lot of things which afterwards cause you a loss of performance. So when you, for example, take a good old COBOL application and you try to transform that into something that runs in a .NET or Java environment, typically the servers that you're going to need later on are much bigger than the ones you originally had. So automation brings performance challenges with it. But there is one drawback of this generative approach, which is much more fundamental and reminds of some of the challenges we had some 40, 50 years ago when this industry was at the very beginning, when the first attempts were made to automate programming, generating the first compilers on the planet. Well, the first programming environments that used such a higher level abstraction to specify software, they didn't come right away with the debugging infrastructure that you need for testing and error detection. So whilst you could specify your software at a relatively high level, one that was certainly higher than the machine that was running the software, well, when something went wrong, you needed to look around in the core dumps to figure out what was actually going on. And we have a little bit of a similar situation now with all the model-driven approaches that we have yet again lifted the level of abstraction, something that we think is great and is desperately needed in order to use models as communication artifacts between the business users and the engineers that need to implement software. But at the same time, if you generate something for the machine at a different level, even if it is Java or C or something else, you tend to debug at a different level of abstraction than how you think and specify your software. We tried it, we fell on our nose. The nose was pretty bloody, I can tell you. We've gained all the good and bad experiences with that approach that one possibly can get, and finally we only could escape to what for most people still today is a rather radical but very consequent solution. What we attempted was to close the gap and raise the level across the entire life cycle. So not only the specification, but also the implementation, testing, debugging, production, to lift this to the model level. Essentially, we had to create that last missing piece, which would allow us to test and debug also at the model level. So this is something which has taken quite a while to implement. The idea is rather quickly born, but putting it into reality is not that easy. Now, when I say that, then I can also say that we have now experience with this type of an approach, model-driven security of about 5 years, but model execution in the way I just described, we use since 2001, 2002. The first opportunity that gave us a really good shot at maturing this approach and technology in an industrial context in a large-scale project was during the merger of the Swiss Bank Corporation and the old UBS to form the UBS that we know today. So this was applied to create the data persistency layer for all retail banking operations at UBS, and is still used today. So there we have built about 800 software services that are entirely specified and executed in form of UML models, which has given us tremendous speed and agility, because you know, when you implement changes, it's much easier to find your way around, because you walk around permanently in your specification and in your design concepts. So it's not like you're trying to search the person that has implemented this particular code, and if that person has moved on to another project or has left the company, then you are in a difficult situation. So we got very good experience there, started to industrialize it the years thereafter, tried to apply it to various problem sizes, various industries, etc., etc. So today, the most prominent types of users for this technology are, you know, financial services, is a very natural conclusion from our own roots, but then secondly, also the energy and utility space, which as soon as we come to the topic of including security in the discussion, they have as high or probably even higher requirements in terms of security as the financial services sector do, because of these own concepts, etc., etc. So what kind of artifacts are we trying to describe? Very easily put, we use only 5 or 6 of the classical diagram types. We've selected UML as a standard because it's universally accessible. Since 2000 it has really seen a lot of adoption, and OMG claims there are about 2 to 3 million developers that understand UML. They may not work with it every day to a very deep level of expertise, but at least it's understandable and sort of a lingua franca of design. So we try to use that fact that graphical concepts are so much easier to communicate between the various stakeholders, because I think in software development we have not only the engineers that are concerned, but also the end users that attempt to specify what the developers should develop. But then we have also in the IT realm, we have different roles. We have project managers, we have security staff, we have the engineers that develop the functional aspects, we have the test and QA departments, and we have the production side. So we have a variety of different stakeholders that should be able to participate from beginning to end. It's something that is not so easy to be achieved, but something that we eventually got to. So it all starts with being able to specify what are we going to build. The second element that we use is the diagrammatic display of data structures, but not only that. We also use class diagrams to communicate how data needs to transform into each other when we have data integration scenarios such as master data management, etc., etc. All the dynamic aspects, you know, the logical behavior, all types of flow information, state engines, event handling scenarios, all these aspects are dealt with at the level of state and activity diagrams. And then last but not least, as I said before, we wanted to include the entire life cycle. That also includes the notion of componentization, of packaging, and of course, last but not least, deployment. And that is also where we use models to specify the physical imprint of how we are going to use the software that we're creating, and then to automate the process of installing components as they change throughout time into various environments, for example, from development to testing, from testing into production, etc., etc. So this is all specified at the level of models. And I give you concrete examples very quickly so you get a more visual impression of what that means. Last but not least, I mentioned before that one of the crucial problems we had to solve was coming up with an idea how we can debug models, and that is eventually what we succeeded in adding at the end. Here, literally what we do is when we go from the models into the execution environment, there is no graphical context anymore, but if we want to debug, we need to recreate that. That's exactly what we do, so that the developer and all other stakeholders can really see what is going on end to end across the software lifecycle. Now, I just want to put in a hook here as to where this becomes relevant for model-driven security. Of course, these are all the artifacts that we are going to use in order to specify security policies, how we are integrating identity and access management, all these various things. These are the tools that we can use for that. And one particularly interesting point is, and from the perspective of the security teams, one of the most frustrating things is that the business users always take for granted that security is taken care of. But it's added only relatively late to the discussion. And this is really a possibility, you will see that later on very concretely, where the security requirements can really discussed at the very earliest stage of the life cycle, whilst it is specified what we're going to build. So for any given service, from a service-oriented architecture, for example, you can sit together right from the start with the eventual user or the stakeholder that it is most interested in getting this functionality working. You can discuss the requirements of security right from the start. They're modeled right from the start, and in that sense, use case diagrams are already runtime relevant. Roles are described at this level, etc., etc. So this is how the life cycle eventually looks like. It's quite interesting, and it's a little bit different to how you're typically used to see a software development life cycle. Of course, you design, you implement, you test, and you run, but the emphasis and where the time is really spent is different. We can mainly consider 3 stages of where our project may be. One is I call it process design, but it concerns much more than just looking at processes. But this is essentially a design phase that is highly collaborative, where the people that are in need for a new software infrastructure discuss with the technicians that are eventually going to implement that. So that is the requirements gathering process, which essentially results in one common shared blueprint. If you have a business process that is being specified, then this is not a separate artifact which is just a design inspiration. No, this will be the highest level of execution view. The IT view will then gradually refine and add more detail, because from an implementation perspective, one needs to be concerned with many different aspects that a business person would never care about. A business person is perfectly content with looking at a very non-granular level at functionality, but from a technical level you need to worry about the details of the implementation. So this is something which is addressed later on. Here in this phase, which is the second one, where the bulk of the work is happening, this is where literally across the stack, and not just at the process or orchestration level, but in our case with this UML execution approach, literally down to the operating system, the software is modeled out with a level of efficiency that we identified over time to be as efficient as if you were coding something. And in the end, of course, this produces a piece of executable UML model, which is run in a virtual machine, just like Java virtual machine is driven by Java bytecode. We create UML bytecode. It's a very similar concept, and this is platform independent. So the same model will run on Windows, Linux, Solaris, and whatever you prefer. What is mentioned in gray here are all phases that are crucial to the entire life cycle that are usually completely automated. For example, if we want to bring in connectivity to another application, let's say SAP or Oracle or something like that, then the interfaces are being imported and automatically redocumented in UML. So for example, connectivity to an SAP system, we would go and analyze the data dictionary of the actual application, extract that information, retransform it, and visualize it as a UML class diagram if we're looking into the data structures, or then of course the service wrapping, the automatic transformation into web services is also something that is dealt with in an automated fashion. Then of course, once we have finalized specifying the design which is now getting more and more granular to really encompass the entire software. Then of course we go through the traditional steps of compiling, deploying, etc., etc. It's just that the input that we use, many of you might ask, well, you start with graphical models, so how the heck do you get executable code out of that? Well, it's a whole lot simpler than you might think, because UML models, although graphically displayed, they are stored on disk in XML. So what we do is we've created a compiler which takes this XML standard, it's called XMI, XML Metadata Interchange, and we built a compiler for that. So the user or developer is presented with a graphical view, the machine is presented with an XML dialect that is relatively straightforward to transform in a very similar fashion as you would transform Java into something that runs, or C into something that runs. We use very similar concepts here. Okay, then let's move on. Just a quick look at what are the infrastructure components that we're looking at. Well, first of all, we need a development environment. The good thing here is that we can use commercial modeling tools that are already on the market. A company that we work with very closely here is NoMagic, produces the very widely used tool Magic Draw. And what we do is we enhance the modeling environment with those capabilities to turn design models into runnable pieces of software. So we have the debugger called analyzer, compiler, we have the importing capabilities for all the interfaces. And then if you look at the runtime side, we have this virtual machine which accepts the compiled output and runs it like any other piece of software is run. Even if you would start in Java, you put it on the virtual machine in form of bytecode, and that's it. In our case, the input is just a different one, but the concept is very similar. Naturally, there are mechanisms to control the life cycle, start and stop services. This is something that you need in any case. One of the important things, and this is also important for the security discussion we're going to have just in a second now, this really has been built with connectivity and integration of disparate and dispersed and distributed software systems in mind. So the idea is not to create a monolithic application, but really to work in a heterogeneous environment where everything that's created new needs to take into account what is already there. So to just illustrate that a little bit more, this is how a use case diagram would look like. You specify who is the consumer of a particular function, what's that function called, what kind of backend systems, for example, are accessed. And later on you will see how this will transform very easily into something that's security relevant. I'll show you that afterwards. This is how a data structure would look like that we have, in this case, extracted automatically from an SAP system. And this is already executable in this form if we combine it with the relevant artifacts on the dynamic side. I mentioned also that we need to take care of data integration. So oftentimes the information that we need also for security purposes, and in order to make appropriate decisions, is this person allowed to access this function or not, for example, we need to collect information from a variety of systems that, just if you look at this case, here we have 3 backends that all deal with an object which is called customer, and they all, understand something different about it. So we need to harmonize that, and that's what data integration is about. Here, this is displaying how these various different views on the object customer are actually relating to each other, how they map into each other. These mappings can be very simple one-to-one relations of attributes, but they can also be very complex because to those mappings we can attach rules that go into any level of complexity, even include decisions that need to be made. They might even involve human intervention, etc., etc. So it's quite some flexibility as to how these transformations are being done. Next point, now we move on to the dynamic aspect. Now it's about logic, it's about how we actually talk to the backend systems. Here you see, and it seems like SAP is a favorite example of mine, as it happens to be this example here. Here we have the direct communication to the SAP system. This is how the data is prepared to go into the SAP system to formulate the request. And here is how we deal with exceptions if something goes wrong. And then finally, this is where we collect the data coming from the backend system. And this entire low-level connectivity service, this has, of course, an input, which is in this case a customer number. And it will produce, as a result, all customer information as found in this backend system. That's all there is to it. There is not a layer below that. That really encompasses the connectivity, etc. There is one concept that we developed over time which helped us a lot in simplifying, specifically in very heterogeneous environment, dealing with various types of backends. So, for example, here we now talk to an SAP system. If we were to talk to a database, it would almost look the same. The difference would be that we have a different stereotype, a different flavor of backend that we call, but there's the same abstraction for all types of backends. So that's really a strong simplification, makes it very effective to deal with. Now, you will say, well, this looks almost similar than the previous one, just a little bit more complicated. Well, that's exactly the idea. At any level of abstraction, we can use the same concepts. Here we look into service aggregation and orchestration. So it doesn't matter whether we talk about a process execution layer or whether we talk about simple straight connectivity to a backend. We use the same tools and expressivity to walk across the stack with those same mechanisms. It's almost the same thing as a for loop. You can use it at a high level or at a low level, it doesn't matter. That's an architectural decision, and exactly that same way we work here. So in this context, we aggregate, you remember this example here, we have information sourced from 3 different backends. Here is how we consolidate that information. So we first have one service call that goes into calls a web service, grabs the customer information coming from there. Then we go into the SAP system, grab what we get from there. Then the third point is we look into a customer data repository in form of a SQL database. We grab that information, and finally we consolidate all these views together. And what's interesting is that, here is specified that there is a sub-activity going on. So there is one level of detail underneath. Well, you guess what is that level of detail? Well, you've already seen it, because this is what is being executed just underneath. And that, again, is the lowest level that we're going to get in terms of implementing this particular use case here. So finally, we move over onto the going towards production. So eventually, we've created our software artifacts, the logic is there, the data structures are there, and finally, we need to decide how are we going to package this, and how are we going to install it on a variety of servers that in the end need to communicate with each other. All decisions that are platform dependent are going to be made here. So this is the physical instantiation, if you like, of what we have designed before. So here is the the packaging artifacts that we have, and here is how they finally relate to each other. There's actually far less drawing going on because those diagrams are generated automatically based on what we want the systems to talk to each other. So finally, I mentioned a couple of times one of the fundamental problems to solve here was how do we do testing and debugging. I mentioned it a couple of times. This is how it looks like. This is the highest level of how you, for example, if you created this use case, this service that we've just specified, this is how it is visualized, what is actually going on. Now, here you see clearly the the individual participants in this particular use case. We have the client, we have the integration element, we have the web service, the SAP system, and the database that we're collecting information from. And here you have the actual services we've implemented. Now, if this were not just a slide, but the interactive system, a double click on this arrow would lead me to this. but now in the view that we've encountered at runtime. So all mistakes that we've made would be visualized in the model. Plus, I would get to every single step we do here exact performance information. I mentioned performance is always something critical. We try to build this from the get-go to deal with extreme transaction handling. Just as an example, at UBS, these are about 35 million service requests we do during office hours on a busy day. And we have a user concurrency of 3,500 to 4,000 users that are using such type of services. So it needs to scale. And for that, to be able to control that, we need to provide very accurate feedback as to where we're losing time in our design and our implementation. So this is something that gets included then in the debugging step. And of course, we are populating all these receptacles where data is passed around with the actual data. So if we have a transformation problem, the mapping wasn't quite right, this is quite straightforward to actually identify those problems and see, this has been going in, this has been going out, we can compare it and move on. The experience we made is that with this approach, still in order to solve a problem or to fix a bug, it depends on the complexity of what has gone wrong. But we found ourselves previously working with normal source code based approaches. We found ourselves sometimes in a situation in a distributed environment that, for 2 or 3 days, you're trying to find out, where has that transaction gone wrong? And then you very often revert to the oldest fashion of debugging, which is putting print statements in log files in order to see, how far can you go. Now, with this approach here, we typically, I wouldn't say within seconds, but within a few minutes, you know exactly where the problem is located, and that gives you a chance to fix it, because we try to aggregate all the information from the distributed landscape together. So we were here, you can repeat the same spiel with every single one of these levels, and you can go through the entire stack and analyze what is going on. Okay, now, how does this all relate to security, you're asking? Well, in fact, what we have done, and this is also a little bit born in practical experience, and it comes certainly from the phase when we were end users buying software. One of the most frustrating things that we found as end users is that every single piece of software you buy has its own security philosophy that it brings into your environment. Now, if you're responsible for security, and our co-founder and CTO, he was in charge of security. That's one of the most frustrating things. If you get dictated by a vendor how you have to do your security around one application, because you want to have a holistic approach that deals with it, in the way that your organization needs to deal with security. If it's a bank, there's tough levels of security. Depending on the industry or the use case, you need to be able to decide for yourself. So what we didn't want to do when we were over time transforming into becoming a product company ourselves, we didn't want to do the same thing and just say, well, this is our version of security and you all have to live with it. But we wanted to say, well, we assume that the organization already knows how security should be dealt with. There are policies in place, they try to be enforced, etc., etc. So what we need to provide is a framework where that approach to security can be integrated with the application landscape. And so in order to do that, because that's a tough development approach, to extract all the application-specific security, put it into one place, we combine all the concepts I've just been telling, using those for developing the security aspect. We combine that with a so-called security interceptor approach. Because there is, of course, one other tiny little problem that we felt we needed to address. In real-life organizations, typically security is done by another team than the functional development. Now, in reality, they do not necessarily, although on both sides you have engineers, they do not necessarily get along with each other so well, because one side tries to force the others to do things in a particular way, and the other guys, they feel they are, they have not the liberty and the freedom to express themselves. They always need to worry about security. So you get 50-page or even thicker documents with guidelines about how you have to code, etc., what you can do, what you cannot do. And it works against the human nature. And it gets particularly bad when business is putting pressure on going live with a particular project, and security staff says, yeah, no, we're not done with our code reviews yet. And the functional developers, they say, yeah, we would be ready to go, but you know, these guys are still doing their security checks. So this is a dampener on organizational productivity. So one thing we thought about for a very long time as well, for a couple of years, is isn't there a way how we can truly separate these two worlds, so that security stuff, they can, in a single policy enforcement point, define how security needs to be done, how access control needs to be handled, how encryption, decryption needs to be handled, etc., how tokens are being generated, and so on and so forth. And let the functional developers just be able to assume that whatever they get as data is sanitized, is okay. You know, it has been checked. Once you get to the stage that functional code is being executed, then you know you can do your thing. And as the function is left, that you know the second part of the security interceptor takes care of cleaning up again. For example, if a document had to be decrypted in order to be worked on, then automatically leaving the actual functional part of the design, then the re-encryption is automatically going to be done. In that way, we wouldn't have to deal with code where security practices and actual functional elements are constantly intermingled. So the idea is that you really separate those two concerns, and I say deliberately separation of concerns, and not just separation of security aspects, because there is a lot more that is cross-functional. For example, logging, billing, all these types of things. You eventually want to put in one place that can be easily audited, supervised, checked for compliance, etc., whereas you don't need to worry that the functional code is constantly touched because you're changing your security policies every once in a while. That is certainly one of the biggest time savers if those things can be separated. This interceptor approach also gives us another thing, that if we change the policies that we're applying here, they are transparently, holistically, and consistently changing for all functional services in use. There's not a single service that we need to touch and check, does this work now? No. We can change the policy in one point, or in several, if this is a design requirement, to dislocate certain security concepts. But again, it's in a defined place and much easier to deal with. So how can we fold this aspect-oriented way of dealing with security onto what we have just learned before, model-driven development? Well, that's why I refer to what I said before. We deal with the identification of the security requirements already at the level of the use case. And you remember probably the first example, if I go back here, we have not specified any particular distinguishment between roles and different levels of access. Well, here we do. It's a very simple example. It's an example that's even out of the school book, if you like. So we have two roles of users. We have a normal employee. The operation A is read product information. Operation B would be write product information. You need to have different level of access in order to be able to do this. So the supervisor is the required role to do that. Now, by drawing a so-called security zone around those services that need special treatment, we are identifying exactly what level of treatment they need. What this little box here, it doesn't seem like much, but in the background it produces automatically a framework where we have the setup that goes through the interceptors, and there is always, they come in pairs. We have a pre-processing interceptor, so before the actual functional code is being called, and we have a post-processing interceptor that jumps into action as soon as we've finished with the functional aspects. How this looks from a call structure is, if you see those different colors here, they have the following meaning. You know, here we have the individual components that are being used. Here we have the actual user. Here we have the infrastructure that provides the security framework. Here we have, maybe it's on the same system or a different one, the security interceptor, which enforces the policy. And here we have the actual business application, which could even be hidden behind an ESB or some other type of infrastructure. So here is the actual invocation of the service. Well, we've added so-called chaperones around this. This is the pre-processing interceptor, this is the post-processing one, and this silently happens for every service that is within this secure zone. Is that clear so far? Yeah, okay. So this is how this works, and now we can apply all sorts of concepts to this interceptor. This is just a list of suggestions of what you might include there. Of course, the idea is not in all cases to really develop this out. The idea is that you have already an identity access management solution, and you are going to integrate it this way via the interceptor and apply it transparently to the service landscape or to the vertical application silos. Authentication, authorization, encryption, decryption, security event management, something that's really hard to do. You know, there are typically different solutions that address security events, like wrong usage or unusual usage patterns, even though a person might have been authenticated and authorized to do something. So you usually use different software packages to do that. Well, this is the place, the interceptor, where you can integrate those together according to rules that you specify within that framework. But also other things like logging, billing, all these things, and you know, I'm sure that you get other ideas depending on your usage background, what you might want to put there. Again, it is not something where we enforce a particular way of doing things, but we just put aside the framework where those aspects can be dealt with in a way that we keep those concerns separated, the functional ones and all the cross-cutting concerns. So all this is integrated in one place, or in as many places as you choose, but they're defined so that we truly have a or several policy enforcement points. Now let's get to a couple of examples, and I've deliberately chosen a few that use this for totally different things. The first one is a company called Intrum Justitia. They are doing credit management, debt management, debt collection, etc., etc. So they're quite successful here in Switzerland. I believe they have 70% market share. Lots of large companies work with them. We typically get in contact with them one way or another. If we don't pay our bills, then all of a sudden these guys are around. And so they had quite an interesting challenge. Their cash flow management is a highly sophisticated application. You couldn't just buy this off the shelf somewhere. It contains so many different rules. They work in different countries where the regulations and the law is different in terms of how you do cash collection and debt management. So this was a legacy application which was written in PL SQL. It had grown over 10 years. It was almost growing beyond recognition. When things had to happen fast, the same ideas were implemented in different places. Sometimes you had the same concepts implemented at the level of the user interface or in the logic part, or even as database triggers. So it can hardly get worse. So they found this was a severe dampening effect on their growth plans, and they wanted to rejuvenate this application, in other words, modernize and redevelop from scratch, basically. Because what they do is very much process driven. They were actually the first company in the world that used the infrastructure that I described to use process models defined by the business to execute on the runtime side and develop the entire application across the entire stack. So this is essentially an ERP system consisting of 1,000 or 1,500 executable UML models, which are modeled across the specification, coming in this particular case from ARIS, the process modeling tool. And so they've analyzed the source code of the original application, and then they have synthesized both concepts, the to-be concept and the as-is implementation, into one, which they put into this UML virtual machine, which is now eventually driven by a number of process clients and is interacting with a number of backend systems. They still kept Oracle as the main database. Now, what have they used this interceptor concept for? They mainly apply it to all the non-functional aspects, such as transaction handling, logging, etc. So it's these types of things. So they have a user community which is very clearly defined. There is almost only one single role, so there was no need for a very sophisticated identity access management solution. It's, these are a handful of people which do the same thing all day long, and this application is for them. So, however, transaction management and handling of those things is important to be clearly structured, because they eventually need to be able to go through an audit and need to prove, how do we deal with these kinds of things. So they used it for that. Actually, if you're interested in this particular case, Gartner wrote a very detailed case study about this, because it is quite unique and the first of its kind, and I'm quite sure you find it on the Gartner homepage. If not, just let me know and I'd be very happy to provide you the link. So this is one use case, transaction handling. The second one is, now we move into the energy space. One of our clients is a company called EVN. They are an energy distribution company, and I think the second largest one in Austria. And the business case here is that they wanted to give the population essentially a direct portal level access to self-manage their energy consumption data. The interesting thing is here that we see a totally different pattern in comparison to the interim case. Here you have two levels of dealing with security. You have two security zones, a DMZ1, DMZ2. The front end is a content management system, and the first level of connectivity, which is actually the proxy on the ESB side, is tunneled through HTTP. And all this needs to make sure is that the only application and the only port being used is the one they have let open, and the one that comes from the content management system. Now, that doesn't mean that behind they don't want the flexibility to be able to have all the different services use different ports. That's exactly the flexibility that they gained from using this interceptor approach that I just described, because essentially there are two types of users. One is a registered user, so it's easy to identify who this is. And then they have the possibility, if the user wants to stay to a certain degree anonymous, they just use three different Kennzahlen, key indicators that uniquely identify a particular person without specifying the name. And for example, contract number or these kinds of things. So all this information is passed on in the protocol header. And then we use here on the backend side, it's not happening in the proxy, but here in the infrastructure that is at the same time also the enterprise service bus, we are deciphering exactly what role is met by a particular user connecting to the system. And via that role, then we use a database-driven access management system to look up, is this user authorized to do that? And based on that, it's decided what this particular user has in terms of rights, which services can be accessed, etc., etc. So as you see, it's the same concept, the same infrastructure being used, but a totally different use case. Now, the one organization, and can unfortunately not go into much depth here, but I can just mention in as much as the information is publicly known. Probably the organization currently using this approach at the most sophisticated level that we've ever seen is Swissgrid. You know the unbundling. You work in the energy space now, so you're familiar with what's going on there. And you know, everything that was previously in a well-controlled environment, well, the entire energy distribution value chain is completely breaking up. You know, this unbundling has fundamental consequences. It's not so easy to enforce security, access level policies, etc. when all of a sudden, you know, you can access it from everywhere in order to participate in the trading of energy, etc., etc. So they have chosen exactly this approach to deal with essentially two types of security communication. One is everything that is related to physical people accessing the system and the rights they have, possibilities they have, but it's not just an identification of is this the right person, is also, you know, is he sitting on the right machine. All these kinds of things can be specified and dealt with in order to enable access to a particular service. The second type of interceptor, so there are two families. You remember the security zones that I showed? Essentially they have two. They have one for human to system communication, which goes through an identity access management system. At the time, I believe it was based on Siemens. I think they are about to change that. Not exactly sure. In any case, the change only needs to happen in one place, in the interceptor, so that should be relatively easy. The second security zone that they've created is for all inter-machine or inter-application applications. For example, they do with exactly the same infrastructure that does the security intercepting, they do the master data management. So they do the data transformation. For example, all the user information is stored in the CRM. I believe this is Salesforce.com, so it's even an off-premise solution. And then they use that information to shuttle it through to the ERP, which I believe is Axapta from Microsoft. So there they have, because there is no human intervention going on there, they have a lighter version of this interceptor, which is much more high performance, etc., etc. There are pretty good ways of dealing with performance, like you're free to define whatever mechanism you please. If you want to give out security tokens that have a time to live for a specified time, this is also the place, the interceptor, where you can put this away. So, in conclusion, and I believe time-wise we're also more or less on track. I said before I'm a little bit biased. I'm really passionate about this whole business of clear separation of concerns, etc. It's really a fundamental thing that we try to address. So here is our list, or my list, of benefits that we see in such an approach. The first thing, and it is the ground principle, that we use here a mechanism for software development where really the design artifacts of how we develop software, they are first-class citizens throughout the entire life cycle. It makes it so much easier to engage all stakeholders at the appropriate level, of course, in the communication required around creating software, including the security aspects. So design equals production. Documentation equals code. This is something which we fought for a long time, and which we believe we have reached by offering this capability of executing UML models at very high performance in mission critical environments. The second element is this is really an approach which is going across the life cycle. There is no real break in the tool chain. There's not all of a sudden you need to figure out things on your own. This is really taking care of a view of the life cycle where a simple change going from end to end, from changing the specification, implementing it, testing it, going live, could happen within just a few minutes. We all talk about agile software development, but agile is quite often done by sacrificing design and architecture, because things are so quick. You tend to forget that there is an architecture. Not in this case, because this allows you to have an architected agile approach, because consistently the important elements across the life cycle are falling in place. What I mentioned also is, I said that before, an unfortunate thing is we come out of the integration space, and security was always important to us. These are, integration and security are always touchy subjects. They are important, they're crucial, but nobody really likes, at least on the business side, to talk about these things. They're just taken for granted, and in reality they are not. They are what define our profession as security specialists. So while usually security comes way too late into the discussion, this approach really moves the security discussion to the very start of the life cycle in a very natural way. And we feel this, this brings much more awareness about the needs of security topics into the relevant stakeholder discussions. A clear separation of concerns. I think this is one of the most fundamental benefits here. It relates to the latest point, which is the gain in organizational productivity, but not having the functional developers and the security engineers standing on each other's foot, because that naturally happens if these two concepts are intermingled. A holistic, consistent approach, that is mainly due to the interceptor approach, which extracts all the security or cross-functional concerns into one place that they can be easily dealt with. And of course, this unity of documentation and code, well, it means a lot in terms of enforcing governance, compliance, auditability, because if you look at how organizations go about compliance and governance and auditing, etc., the issue is that you may have a certain type or set of documentation of your processes and procedures, but they're printed out in binders. There's not necessarily a guarantee that this reflects the exact state of how the production software is currently used. With this approach, where both views are, you have the runtime view and the documentation view, but they are in fact inseparable, you always have the guarantee that you're actually looking at the process or the function the way it is running. So what we hope naturally is that the classic phenomenon of so-called legacy software, which we typically refer to as software that is not documented as it should be, or the developers that know how it works are long gone. It happens here and there, every once in a while. And we certainly hope with this approach that we can eradicate and eliminate this problem altogether. It doesn't mean that you cannot model as bad as you can code bad. Still there are quality concerns at the level of how an individual is using it. But given the power of communication, graphical models, it's far easier to recognize what is a good design and what is a not so good design. With code, you shut out lots of stakeholders out of the discussion, and it may be good, it may be not. There's no way to tell apart for the engineer who actually built it. With that, I would like to conclude, give you some contact information. Feel free to contact me. I see this as a discussion subject. I'd like to hear your views. I'm going to be around for the dinner as well, but also afterwards, absolutely no problem. You can find me here, and this is E2E is the company I work for. We have some information there as well, case studies, etc., if you're interested. Thank you very much for your attention.